Welcome to physical chemistry. Imagine a busy train station during rush hour with people moving in all directions at different speeds. The molecules in a gas behave exactly the same way inside their container. Today, we are going to explore molecular velocities and kinetic energy. We will learn how to mathematically describe the chaotic swarm of particles in a gas and how understanding their speed helps us figure out exactly how much moving energy the gas holds. Let us dive in. Now that we have pictured our busy train station, let us look at the molecules themselves. In physical chemistry, we cannot track every single molecule because there are trillions of them in even a tiny bubble of gas. Because they are constantly colliding and changing directions, they do not all travel at the same speed. Some are incredibly fast, some are sluggish, but most travel at a moderate speed. Instead of tracking individuals, we use statistical averages to describe the speeds of the gas molecules as a whole group. Scientists use three specific types of velocities to describe a gas, and each serves a different mathematical purpose. To understand these statistical averages, let us start with the first type of speed. This is the most probable velocity. Conceptually, if you picked a molecule at random, this is the speed it is most likely to have. The formula is the square root of 2 times r times t divided by m. R is the universal gas constant, T is the absolute temperature in Kelvin, and M is the molar mass in kilograms per mole. As the temperature increases, the molecules gain energy and this velocity increases. Conversely, heavier gases with a larger molar mass will have a slower most probable velocity, simply because heavier things are harder to move. Moving on from the most probable speed, we have the average velocity. This is exactly what it sounds like, the simple mathematical average of all the individual speeds added together and divided by the total number of molecules. The formula looks very similar to the previous one, but it includes the number 8 and the mathematical constant pi in the fraction. Because the number 8 divided by pi is slightly larger than the number 2, the average velocity is always slightly faster than the most probable velocity. Heating the gas will cause this average speed to rise, while using a heavier gas will cause it to drop. Now that we have seen the first two speeds, we arrive at the third and most important one for calculating energy, the root mean square velocity. Conceptually, this is found by squaring all the individual speeds, finding the average of those squared numbers, and then taking the square root. In the formula, the numerator contains the number 3 instead of 2 or 8 over pi. The variables r, t, and m retain their exact same meanings. Out of the three types of speeds, the root mean square velocity always results in the highest numerical value. If you double the temperature of the gas, this velocity increases by a factor of the square root of 2. Before we calculate anything, let us visualize how these three velocities relate to one another on a graph. What you are seeing is the Maxwell-Boltzmann speed distribution. The horizontal axis represents molecular speed and the vertical axis shows the number of molecules. Notice the shape of the curve. It has a long tail stretching to the right. Because of this tail, the few extremely fast molecules pull the average and root mean square velocities to the right of the peak. The peak itself is the most probable velocity. The root mean square velocity is always the furthest to the right, meaning it is always about 22% faster than the most probable velocity. Now that we understand what the root mean square velocity is, let us see this with a concrete example. We are asked to calculate the root mean square velocity of nitrogen gas at a specific room temperature of 300 Kelvin. This is a standard calculation that helps us understand the physical behavior of air. We know our universal gas constant is 8.314. The temperature is already in Kelvin. However, we must be very careful with the molar mass. Nitrogen gas is 28 grams per mole, but we must convert this to kilograms per mole by dividing by 1000, giving us 0.028. Finally, we write down our governing equation so we know exactly where to plug in our values. Continuing with our calculation, we now substitute all of our known numerical values into the equation. We place 8.314 in place of the gas constant, insert 300 for the temperature, and put 0.028 in the denominator for the mass. After multiplying the numbers in the numerator and dividing by the denominator, we take the square root of the result. This gives us a final answer of approximately 516.9 meters per second. Physically, this means that at room temperature, nitrogen molecules are zipping around at over 500 meters every single second, which is actually faster than the speed of sound. Having calculated how fast these molecules move, we can now explore how that speed translates into energy. Understanding kinetic energy is absolutely crucial in the real world. It explains why hot air balloons rise and how car engines generate power from expanding hot gases. The velocity we just calculated directly determines the translational kinetic energy of the gas, which is the energy of moving in a straight line. For monoatomic gases like helium, this translational motion represents their entire thermal energy. Polyatomic gases like oxygen have additional thermal energy stored because they can also spin around and vibrate like a spring. But for all gases, temperature is the key driver of this motion. This brings us to the mathematical formula for kinetic energy. Conceptually, this formula shows that the kinetic energy of an ideal gas depends entirely on its temperature, regardless of what type of gas it is. This specific equation calculates the total translational kinetic energy for one entire mole of gas. The symbol EK represents the kinetic energy in joules per mole, R is the universal gas constant, and T is the temperature in Kelvin. Notice that mass does not appear in this equation at all. If the temperature increases, the kinetic energy increases proportionally. If you know the temperature of a room, you know exactly how much energy the gas holds. Following the energy per mole, we can also find the kinetic energy for a single, individual molecule. Conceptually, this is the exact same energy, just scaled down to the microscopic level. The formula looks almost identical, but instead of the universal gas constant R, it uses the Boltzmann constant, represented by the symbol K. We get the Boltzmann constant by dividing R by Avogadro's number. The temperature T remains exactly the same. Because a single molecule is so incredibly small, the Boltzmann constant is a very tiny number, meaning the energy of one molecule will also be a very tiny fraction of a joule. But just like before, heating the gas increases this microscopic energy. Now that we have our energy formulas, let us apply them to a second example. We are asked to determine the kinetic energy of helium gas at a standard room temperature of 298 Kelvin. We need to calculate two different values, the energy for an entire mole and the energy for a single molecule. We chose the first formula because it uses the universal gas constant for molar calculations. We substitute the fraction 3/2 with the decimal 1.5 to make the math easier. We plug in 8.314 for R and 298 for the temperature. We will solve this first and then move to the single molecule. Continuing with our calculation, multiplying the first set of numbers gives us 3716.3 joules per mole. This is a substantial amount of energy hidden in the microscopic motion of the gas. Now we switch to the formula for a single molecule using the Boltzmann constant. We substitute 1.5, multiply by 1.38 times 10 to the negative 23rd power, and multiply by the temperature. The final calculated value is 6.17 times 10 to the negative 21st joules per molecule. Physically, this shows that while a single molecule holds an incredibly small amount of energy, trillions of them together create massive macroscopic power. Now that we have used this formula to calculate energy, let us understand where it comes from. We begin our derivation with the kinetic gas equation, which connects macroscopic pressure and volume to microscopic motion. We also bring in the well-known ideal gas law for exactly 1 mole of gas. Because both of these equations are equal to the product of pressure and volume, we can set them equal to each other. The left side represents thermal energy, and the right side represents mechanical energy. This is a crucial step because it bridges the gap between thermodynamics and mechanics. Finally, we multiply by 3 and divide by mass to isolate the square of the root mean square velocity. Continuing our derivation, we now recall the standard classical physics formula for kinetic energy, which is 1/2 mass times velocity squared. Our goal is to substitute the expression for squared velocity that we just found into this kinetic energy formula. When we plug it in, something beautiful happens. The mass terms in the numerator and denominator cancel out completely. We are left with a beautifully simple result. This gives the final result that the kinetic energy of 1 mole of gas is exactly 3/2 R times T. This proves mathematically what we stated earlier. If you know the temperature of an ideal gas, you know exactly how much translational kinetic energy it has, regardless of its mass. We have covered a lot of ground today, so let us reinforce the most important ideas. First, remember that molecules in a gas are in a state of constant, chaotic motion with varying speeds, which we describe using statistical averages. Second, the root mean square velocity is the most critical speed, directly linking the microscopic movement of particles to the macroscopic temperature of the gas. Finally, and most importantly, the kinetic energy of an ideal gas depends entirely on its temperature. Ultimately, the temperature of a room is nothing more than a direct measure of this average translational kinetic energy. Mastering these concepts provides a strong foundation for understanding all thermodynamic processes. Great job following along.